We are looking at a localized concentration of matter that physically should not exist in this form. It is a massive structure spanning over 1,600 light years, packed with roughly 500 million times the mass of our sun. This intensely glowing red smudge is known as JWST-Z14-0. Captured by the James Webb Space Telescope, it sits frozen in a universe that was a mere 290 million years old when this light first began its long journey toward Earthtown. That exact time frame represents a fundamental problem for our standard models of cosmology. At 290 million years post-expansion, the universe was supposed to be a sparse, disorganized environment, barely beginning to ignite the very first isolated stars, let alone complex galactic structures. According to the established laws of physics governing dark matter halo formation and cold gas accumulation, building a unified galaxy of this staggering stellar mass should require well over 1 billion years of slow, methodical gravitational assembly. Yet, the empirical data from the JWST Advanced Deep Extragalactic Survey forces us to confront a wildly different reality.
The matter in this region organized itself into a massive, functioning galaxy with an ultra-efficient speed that defies our current equations. The physical paradox deepens when we look beyond the sheer physical dimensions and examine the specific chemical fingerprints hidden inside this ancient light. The cosmological anomaly here isn't just about raw mass, it is about an impossible level of stellar maturity. When scientists turned JWST's mid-infrared instrument toward the faint light of JADE's GS-Z14-0, they detected unmistakable, powerful emission lines indicating the widespread presence of complex cosmic dust and significant amounts of oxygen. Oxygen is absolutely not a primordial element left over from the initial rapid expansion of the Big Bang. It is an advanced chemical byproduct forged exclusively in the crushing nuclear furnaces at the cores of the universe's most massive early stars. Because oxygen is only dispersed into the surrounding interstellar medium when those colossal stars end their lives in violent supernova explosions, finding it here imposes a severe physical constraint on our timeline.
It dictates that multiple, successive generations of massive stars had already formed from pristine gas, burned entirely through their nuclear fuel, and detonated as supernovae, all within an impossibly narrow window of just 290 million years. Faced with this structural and chemical paradox, the immediate scientific instinct was to suspect an imposter. Initially, many researchers hypothesized that a supermassive black hole might be masquerading as an unusually bright, rapidly forming early galaxy. If a highly active supermassive black hole was furiously consuming surrounding matter, its incredibly dense accretion disk could theoretically produce an intense luminosity that perfectly mimics the infrared signature of hundreds of millions of young stars. However, careful spatial analysis of the JWST imagery revealed that the light of JADE's GS-Z14-0 is distributed evenly across the entire 1,600 light-year span of the structure. This widespread emission decisively rules out a centralized black hole. This discovery does not invalidate the fundamental expansion of the universe.
The foundational framework of the Big Bang remains entirely intact, and the early cosmos was undeniably hot and dense. What is truly broken is our understanding of how quickly matter organized itself inside that expanding space. To see how astrophysicists know this timeline is fractured, we must first prove this galaxy isn't simply a closer imposter pretending to sit at the edge of time.
Before rewriting the textbooks, astronomers had to thoroughly eliminate the possibility of a cosmic optical illusion. In astronomy, Distance is measured by redshift, how much a galaxy's light has been physically stretched by the continuous expansion of space over billions of years. Initially, researchers only had photometric data. This means JWST took images through different infrared filters and estimated the distance based on how red the galaxy appeared. But this method is notoriously vulnerable to false positives, which plagued early JWST discoveries. A closer, severely dust-filled galaxy can easily absorb shorter blue wavelengths and scatter the rest, appearing artificially red to our telescopes. This is a well-documented trap, where an ordinary local galaxy hiding behind dust perfectly mimics a primordial structure. If Jade's GSZ 1448 was just a dusty imposter sitting relatively nearby, the entire timeline paradox would immediately vanish. To permanently break the illusion, researchers needed undeniable physical proof, not just a color-based estimate. They needed to measure the light directly.
To get that proof, the team aimed JWST's near-infrared spectrograph, or NISPEC, directly at the anomaly for 10 continuous hours. They weren't taking another photograph. They were extracting a physical barcode from the light itself. A spectrograph acts like an extremely precise prism. It takes the faint trickle of photons arriving from the galaxy and splits them into a highly detailed one-dimensional graph, revealing exactly how much light exists at every individual wavelength. Hidden inside that graph is the ultimate prize for early universe cosmology, a distinct physical feature known as the Lyman break. This is the smoking gun that mathematically separates genuine cosmic dawn galaxies from low redshift dust clouds. To understand the Lyman break, you have to look at the pristine space between galaxies. In the early universe, before massive stars fully illuminated the cosmos, vast, unlit clouds of neutral hydrogen gas filled the cosmic void. This primordial fog acts like an absolute filter. Neutral hydrogen aggressively absorbs energetic ultraviolet light.
Any starlight emitted by the galaxy below a specific ultraviolet wavelength gets completely swallowed up by the surrounding atomic gas before it can travel far from the surface. This creates a sudden, unmistakable cliff in the galaxy spectrum. All the outgoing light below that specific frequency just drops to absolute zero. When the 10-hour JWST spectrum was finally processed, that exact cliff was clearly visible. But because the universe has been expanding for over 13 billion years, that ultraviolet cliff had been severely stretched. It was dragged all the way out of the visible spectrum, past the near-infrared, and deep into the wavelengths JWST was built to see. By measuring exactly where that cliff landed in the infrared, scientists could calculate the precise expansion rate the light had experienced. This spectral barcode definitively anchored the galaxy at a confirmed redshift of 14.1432. The sharp drop-off left zero probability for a low redshift imposter. While the precise mass distribution of the star system remains slightly blurred at this extreme magnification, the distance measurement is locked in as an empirical, undeniable fact.
We are verifiably looking at an enormous source of continuous starlight, operating just 290 million years after the Big Bang. With the distance firmly verified, we have to look at what the standard model predicted we should actually find there. With the distance firmly verified, we have a profound problem with the cosmic speed limit. If Jade's -GS-Z14-0 is genuinely sitting at 290 million years after the Big Bang, its sheer size breaks the timeline. To understand why, we have to look at the blueprint that built the modern universe. For decades, our best supercomputer simulations agreed that the cosmos built structures slowly, from the bottom up.
This framework is called the Lambda CDM model. It assumes that the universe is expanding and heavily reliant on the gravitational pull of cold dark matter. Dark matter makes up roughly 85% of all the mass in the cosmos. Because it doesn't emit light and largely avoids colliding with normal gas, it acts as the perfect, undisturbed, invisible scaffolding for the entire universe. According to advanced N-body simulations, this dark matter is subject to a slow, tedious physics of gravity. Small, dense pockets of dark matter gently pull themselves together, slowly forming a vast, invisible cosmic web across the dark ages. This invisible scaffolding creates deep gravitational wells.
Over hundreds of millions of years, these nodes pull normal, pristine hydrogen gas into immense clouds. This slow mechanism is known as hierarchical clustering, the fundamental process that eventually ignites stars. The defining rule of this hierarchical assembly is time. You start with small things, and they crash together over billions of years. To build something even a fraction of the size of the Milky Way requires a vast runway of cosmic history. So when astronomers look deep into the early universe, specifically the epoch just after the cosmic dark ages, the structures should be small. Massive galaxies take incredible amounts of time to assemble, simply because gravity works at a fixed, predictable speed. A localized structure containing roughly 500 million solar masses should not just pop into existence. Under the standard model, it should take well over 1 billion years for the dark matter halos to merge and drag enough gas into a single cohesive neighborhood. JADE's GS-Z14-0 violently contradicts this gradual clustering mechanism.
At a redshift of 14.32, it forces a galaxy the size of our cosmic neighbors to form when the entire universe was less than 300 million years old. If the Lambda CDM model is entirely correct about how fast dark matter aggregates, then early galaxies should look like tiny, chaotic fragments loosely tied together. Instead, James Webb reveals a single galaxy already fully formed, massive, and intensely bright. The simulations of the dark matter web remain incredibly robust for the modern universe. The tension lies strictly in the early universe's speed limit. The subgrid physics of exactly how that early gas cooled and turned into stars is now highly uncertain. This anomaly leaves cosmologists with two distinct problems. Either the dark matter scaffolding formed much faster than gravity traditionally allows, or the normal gas inside those early nodes was converting into massive stars with a terrifying, unpredicted efficiency. Recent three-dimensional models of the early cosmic web show just how strained this timeline is. Abandoning hierarchical growth entirely would contradict overwhelming evidence for dark matter.
Gravity still works at a set speed, and assembling 500 million suns takes time. But the light streaming from JADES tells us something far more troubling than just its impossible size. What did astronomers find inside this galaxy that proved it wasn't just born, but had already lived a violent life?
The sheer size of JD's GS-Z14-0 was a massive problem for cosmologists, but its chemistry turned the problem into a full-blown crisis. Astronomers weren't just looking at a large cloud of pristine gas. They were looking at a polluted environment. In 2025, follow-up observations using the Atacama Large Millimeter Array, or ALMA, successfully isolated a specific wavelength of light coming from the galaxy. It was the unmistakable signature of ionized oxygen. They had found heavy elements at the edge of time. This confirmed earlier data from Webb's mid-infrared instrument, which also detected the thermal glow of cosmic dust. The galaxy was roughly 10 times more enriched with heavy elements than standard models predicted for this early era.
To understand why this breaks the timeline, we have to look at how elements are forged. The Big Bang produced only hydrogen, helium, and a tiny trace of lithium. There was absolutely no oxygen in the early universe. Every single atom of oxygen must be cooked inside the crushing core of a massive star through nuclear fusion. But simply making the oxygen isn't enough to trigger the emission lines detected by ALMA and Webb.
To disperse these heavy elements across a galaxy, those giant stars must first reach the end of their lives. They have to run out of fuel, collapse, and detonate in catastrophic supernova explosions. This creates a severe bottleneck in the timeline. The presence of abundant oxygen means that an entire first generation of stars had already formed, lived out their complete life cycles, and violently died. And all of this stellar evolution had to finish before the 290 million year mark. According to our traditional models, assembling enough gas to ignite even the first stars should have taken most of that available time. It is important to note that we cannot see the exact stars that produce this oxygen. We are only measuring the expelled gas that currently illuminates the galaxy. The exact mechanism of their birth remains hidden. To solve this, some astrophysicists suggest the very first stars, known as population 3 stars, were unimaginably massive. If they were hundreds of times larger than our sun, they would burn through their fuel at a terrifying rate. These theoretical giants could live and die in just 1 or 2 million years.
That rapid turnover might accelerate the oxygen enrichment just enough to match the ALMA data without breaking the fundamental laws of physics. But we must be careful with our assumptions. Finding widespread oxygen in this era does not mean we are looking at rocky planets or the ingredients for life. At cosmic dawn, oxygen simply means the debris of dead massive stars. Regardless of how massive those first stars were, the fundamental physics of nucleosynthesis remains entirely correct. The crisis is strictly a matter of timing and efficiency. The gas was converted into stars at a speed that defies current simulations. With a massive physical size and a chemically polluted environment, astronomers had to be absolutely sure this wasn't an illusion. Could a hidden monster in the center of the galaxy be faking this incredible brightness?
To save the standard model of the universe, some astronomers hoped a greedy black hole was simply faking the brightness. If the light from JWST JZ14-0 was just a supermassive black hole aggressively feeding, it would neatly explain the extreme luminosity without requiring a chemically mature galaxy. Black holes themselves emit no light, but the violent friction inside their accretion disks can outshine entire galaxies. If this was an active galactic nucleus, or AGN, the light would be originating from a microscopic centralized point rather than billions of distinct stars. An extremely obscured black hole driving intense jets into the surrounding gas could potentially mimic some extended emission. If this imposter theory held up, the crisis for cosmology would vanish, safely returning our timeline to normal. But in April 2026, the James Webb Space Telescope delivered a fatal blow to the black hole hypothesis. New spectroscopic data revealed intense C3 emission, a specific signature of ionized carbon, glowing brilliantly across the structure. Crucially, this carbon emission wasn't concentrated in a dense core. Instead, Webb's spatial mapping showed the light is physically displaced by hundreds of parsecs, spreading the glow over 1,600 light-years. Because JWST possesses unprecedented infrared resolution, scientists could clearly separate the glowing carbon from the main stellar continuum. This proves we aren't looking at a single point of light blurring into a blob, but a genuinely vast, clumpy, and distributed stellar structure. This massive, sprawling footprint proves the luminosity is driven by a chaotic frenzy of young stars, not a single central engine.
Furthermore, the 2026 observations captured direct evidence of violent galactic outflows, with gas being expelled at hundreds of kilometers per second. Astronomers measured a mass loading factor between 4 and 15, meaning the galaxy is ejecting material at a staggering rate compared to its star formation. This ejective feedback is a direct byproduct of massive stars living, dying, and detonating as supernovae in rapid succession. The specific chemical signatures found in these vast outflows simply do not match the high-energy radiation expected from black hole accretion.
Instead, they perfectly align with widespread, unregulated star formation occurring on a scale that defies standard cosmological predictions. This doesn't mean supermassive black holes didn't exist in the early universe, or even that one isn't hiding somewhere inside this galaxy. It simply means a central black hole is definitively not the primary source of the anomaly's extreme brightness. The AGN theory could only roar back to life if a future space telescope detected a massive point source of hard X-rays piercing through the dust. Until then, the observational evidence leaves us with an undeniable reality. We are looking at a genuine galaxy that somehow converted pristine gas into billions of mature stars in a nearly impossible timeframe. The black hole escape hatch has been firmly locked and sealed by empirical data. If we can no longer blame an active nucleus, then we have to face the terrifying efficiency of these ancient stars. If the standard model is broken, what new physics can possibly explain a galaxy in such a rush to exist?
Without a black hole to blame for the extreme brightness, astrophysicists are forced to rethink how a galaxy actually builds itself. In the modern universe, creating stars is a surprisingly inefficient process. When a giant cloud of gas collapses under gravity, it ignites the first massive stars. But those stars are violent. Their intense radiation and eventual supernova explosions create a massive outward pressure, literally blowing the remaining star-forming gas away. This process is called stellar feedback. Because of it, modern local galaxies only convert about 5 to 10% of their available gas into stars before the engine chokes itself off. But to explain the several 100 million solar masses of JADE's GSZ 14-0, that slow, regulated timeline has to be thrown out completely. This early galaxy didn't gently form stars over billions of years, it aggressively devoured its gas reservoir. Current hydrodynamical cosmological simulations are being actively rewritten to test a radical new mechanism, an ultra-efficient engine. In the extreme density of the early universe, gravity might have simply overpowered the explosions.
Instead of supernovae blowing the raw material away, the immense gravitational pressure of the cosmic dawn could have kept the gas locked in place. This would push star formation efficiency from 10% up to an astonishing 80%. By early 2026, researchers analyzing the galaxy's carbon-3 emission lines calculated massive outflows of material, pouring out at over 160 solar masses per year. This intense mass loading factor suggests we are directly observing the violent, real-time struggle between a hyper-efficient gravitational engine trying to build the galaxy and stellar feedback trying to rip it apart. But there is a second, even stranger possibility being debated. The engine driving this rapid growth might not be governed by gas dynamics alone, but by a fundamental modification to dark matter itself. In our standard cosmological models, dark matter acts as the invisible scaffolding that pulls normal matter together. But those baseline models assume a specific, relatively slow rate of initial clustering. If we are finding massive, mature galaxies this early in the timeline, does that mean the Big Bang never happened? If the true nature of dark matter allows it to clump together much faster in the early universe, it would create deep gravitational wells
far earlier than expected. These accelerated halos would act like cosmic funnels. Some 2026 theoretical papers even suggest this high-density dark matter environment provided the exact conditions needed to bypass normal star formation limits entirely. The invisible scaffolding was simply built faster, forcing the gas to follow. Whether the ultimate answer is hyper-efficient star formation or accelerated dark matter, gravity remains the sole driver of assembly. The scientific debate is entirely over the thermal resistance of the gas. These are the bleeding-edge models scientists are currently using to fit the James Webb data. We do not yet have the decisive observational proof to declare a winner between the two mechanisms, but one thing is certain: the timeline of our cosmic origin story is getting an urgent, massive rewrite. And this sudden theoretical shift has led the internet to ask a much more dangerous question. If we are finding massive, mature galaxies this early in the timeline, does that mean the Big Bang never happened? The discovery of massive, mature galaxies at the dawn of time has triggered a viral panic that the Big Bang never happened. But despite the sensational headlines, the fundamental framework of our expanding universe remains completely intact. What is broken is our understanding of how quickly matter organized itself inside that expansion. Fringe theories have attempted to use these ultra-distant anomalies to claim the universe has no beginning. But that ignores the deepest evidence we have: the cosmic microwave background, the universal afterglow of the Big Bang itself, still provides absolute proof of a hot, dense origin. If the Big Bang was wrong, the light from these early galaxies would not be uniformly stretched or redshifted by the expansion of space. James Webb spectrometers confirm this expansion perfectly. The crisis lies entirely within the messy, chaotic realm of astrophysics. To understand the difference, think of the universe's expansion as the stage, and galaxy formation as the play. The stage is expanding exactly as our standard lambda CDM model predicts. But the actors on that stage, the clouds of primeval hydrogen gas, are moving with staggering speed. Astronomers call this specific problem gastrophysics. It describes the turbulent behavior of gas cooling and falling into the gravitational wells of dark matter. Before James Webb, supercomputer models assumed early star formation was highly inefficient, heavily regulated by stellar feedback. The sheer size and brightness of JWST Z14 proves that assumption was completely backwards. Instead of a slow trickle, early galaxies were incredibly efficient engines. They converted raw gas into massive stars at rates that defy all known modern galactic mechanics. And this is no longer an isolated anomaly. In early 2026, the spectroscopic confirmation of an even more distant record breaker named MOM Z14 proved that JADES was not a fluke. The cosmic dawn was crowded, violently active, and far brighter than anyone predicted. In the modern universe, when giant stars explode as supernovas, they violently blow away the surrounding gas, choking off new star formation. But in these early supergalaxies, the dark matter halos were likely so dense that not even exploding supernovas could stop the machine.
The immense gravity of these pristine dark matter wells forced the gas to keep collapsing, forging millions of solar masses into stars almost simultaneously. This ultra-efficient mechanism explains how a structure could grow so massive and pump out so much oxygen in just 290 million years. So, the foundation of cosmology survives the James Webb Telescope. The universe is expanding, and the timeline of 13.8 billion years holds firm. We do not need to rewrite the laws of physics, nor do we need to abandon the Big Bang. Instead, we are tearing out the entire chapter on the cosmic dawn. The dark ages of the universe were not a slow, gradual awakening. They were an explosive era of extreme efficiency, where the rules of modern star formation simply did not apply.
By separating the expansion of space from the violent mechanics of gas and gravity, we can finally isolate the true mystery. The timeline itself is not broken, but our timeline for when starlight first ignited has been radically compressed. This leaves us with a profound realization. If a galaxy like Jade's GSZ14-0 is already filled with oxygen and the debris of dead suns, it is not the true beginning.
We are looking at a mature cosmic city, but we have not yet found the first pioneers. To truly understand how this ultra-efficient engine started, we must look even further back into the dark. We have to hunt for the elusive population 3 stars, the pristine, giant fireballs that lived and died before oxygen even existed. Because Jade's GS-Z14-0 is already polluted with oxygen, it cannot be the starting line of the universe. It is simply the smoking gun that proves the true beginning was far more sudden and far more violent than we ever imagined. To resolve the tension created by this impossibly mature galaxy, astrophysicists are shifting their gaze even deeper into the cosmic dark ages. They are now hunting within the incredibly narrow window of just 1 to 200 million years after the Big Bang. They are searching for the elusive population 3 stars. These are the theoretical first generation of suns, massive, pristine giants formed entirely from the primordial hydrogen and helium left over from the birth of the universe. Unlike every star we see in the night sky today, population 3 stars contained absolutely zero heavy metals. No carbon to form planets, no oxygen, no iron, just pure, unadulterated gas collapsing into colossal fireballs. Finding them requires capturing a very specific, almost impossibly faint spectral fingerprint. Astronomers are scanning the deep infrared for a pristine spectrum showing intense emission lines of doubly ionized helium, with a complete absence of heavier elements. In early 2026, JWST began returning data from ultra-deep campaigns targeting this exact signature. Observations of a primordial halo region known as Hebe, sitting near the distant galaxy GNZ11, have finally revealed this pure helium emission. This intensely energetic helium signal requires radiation from stars that are hundreds of times more massive than our own sun. It is the closest we have ever come to witnessing the raw, unpolluted ignition of the universe. Simultaneously, through the immense magnifying power of gravitational lensing, astronomers have isolated ultra-compact dark matter halos like LAP-1b. Within these microscopic cosmic pockets, they are finding the exact theoretical conditions required to ignite the first generation of stars. But confirming a pristine, untouched population 3 star remains one of the hardest observational challenges in astrophysics.
These giant stars lived fast and died spectacularly, erupting as supernovae that immediately flooded their surroundings with the very heavy elements we are trying to avoid. They might have been so deeply shrouded by the thick, neutral hydrogen fog of the early universe that even the James Webb Space Telescope could struggle to catch them before their light is absorbed entirely. If we ultimately fail to find these zero metallicity stars, it would suggest the universe somehow synthesized and mixed its heavy elements before stars even formed, a scenario that would completely upend our understanding of cosmic chemistry. But the discovery of Jade's GS-Z140 strongly implies these first stars are out there, hiding just beyond our current reach. Its mature oxygen did not appear by magic. It is the ash left behind by that missing first generation. The cosmic dawn occurred. We just have not yet managed to photograph the very first match being struck in the darkness.
as cosmological models are hastily rewritten, the true edge of space continues to beckon.
As JWST prepares its next cycle of deep field observations, we are finally looking in the right place, armed with the precise chemical fingerprints needed to find them. When we finally pierce the absolute limits of the Dark Ages, will we see the first pristine stars, or something even more impossible?